Okay, so good afternoon, everybody. Today is our great pleasure to have Professor Kyung-Youn from National Zhongxin University, and she is an expert in probability theory. And today she will share with us her recent ideas or results about this kernel estimate and stability under Feynman cut perturbations. So I am very curious about this topic. So let's welcome her.
I'm really honored to be here to give a lecture today. This is my recent research about the heat kernel, which is the solution, the fundamental solution of the heat equation. And then we extend the result into the Feynman perturbation. So let's start the motivation. So I first give the definition of the heat kernel first, and then give the definition of the Feynman semigroup and the motivation. So everyone knows this distribution. So you see this distribution, we call the Gaussian distribution or random distribution, which has the mean zero here and has a diverse radius at the variance. So if the random variable has a normal distribution with mean mu and sigma square, we know that the density of this distribution is described by the exponential function. So we know this Gaussian distribution or normal distribution. And the Brownian motion is the well-known random variable, which is continuous, and it has the normal distribution with the mean zero and variance t.
Okay. Do you mind if we use title? I think it's louder. It's better, right? Okay.
Let's continue. And then we consider the Brownian motion. The Brownian motion is the random variables which have the normal distributed with mean zero and variance t. And it is a well-known random variable to explain the molecules in a water or in a gas. So especially in 1905, the Albert Einstein find the solution. He present the paper with the solution of the following heat equation to describe the Brownian motion. So we consider the Laplacian, which is the summation of the double integrable of each xi's, and we consider some of them, and we call this operator as a Laplacian. And using this Laplacian, we consider the following heat equation, and the starting point at time 0, we consider the initial function as fx. Then the fundamental solution. The solution of this equation is written by the function, this Gaussian distribution function. Okay? And we call this function as the fundamental solution of the Laplacian. So you can see that the same function, this PB with the exponential function with some constant, is called the transition density for Brownian motion, or we call this function as the fundamental solution. So in PDE, we call this function as the fundamental solution, and probability, we call this is the transition density for the same function. So in PDE, in analysis, and also in probability, they both are want to find the exact value of this function. This relation also explained by the generator. When we put the generator as LB, then it is the infinitesimal generator of the Brownian motion. That means the LBF is explained by the limit of this expectation of the function with the Brownian motion minus fx divided by t. This is the definition of the infinitesimal generator of the Brownian motion using this notation. And if we consider this as the utx, then the meaning of this limit is the derivative according to t, where t goes to 0. Then this means the derivative at 0, so that by this observation we change this limit into the Laplacian. And we put this Laplacian, the initial point, we put fx, so that the infinitesimal generator is exactly same as the Laplacian. So these two are really well connected in the Brownian motion. Okay? The Brownian motion and the Laplacian is well connected. What about non-local operator? We consider the alpha stable process, which we call the process, random variable is alpha stable process if the distribution of the process at time t and at time 1 with some time changes has same distribution where alpha is in between 0 to 2, we call this is the alpha stable process. If these two has same distribution, then we call this is alpha stable. Especially alpha equal 2, it is the Brownian motion. So you see that where alpha equal 2, which is the black one, which is the light tail, the small tail, this is the Brownian motion with the exponential decay. We see that previous slide that this decay exponentially. So if the distance x is very large from to the mean, then it's decaying fast. But if alpha is in between 0 to 2, we see that in this case, if alpha goes to 0, then we have the heavy tail. And this decay polynomially. So we want to find the explicit distribution density for the alpha stable case, where alpha is less than 2.
Why do you call this stable? Alpha stable.
Oh.
I know the meaning of alpha, but I don't know the meaning of stable. Why do you call
This table means that they have the same distribution according to this time changes.
By the scaling.
Scaling. So in case alpha equal 2, also we hold for the Brownian motion or fractional Laplacian. But
How about if alpha is bigger than 2?
it also holds in if the space are changes. In Euclidean space, we only have this property, but if alpha equal 2 in the spatial space, this also holds for the bigger alpha. So there are also some result on that, but in this today we only discuss about the alpha less than 2. Okay. So now we consider this alpha stable case in analytic point of view. In that case, the generator or corresponding operator not anymore diffusion, but it is the non-local operator with the kernel 1 over x minus y with d plus alpha. So this is the infinitesimal generator of the alpha stable process, and we also consider the equation using this operator. And we can get the Higgs kernel estimates, which is the only we have the upper and lower bound, which are same terms. We do not have the explicit estimate for equation for this function, but we only have the upper and lower bound, which means the minimum, I use the notation wedge to denote the minimum, and the minimum of the time variable and times with the kernel. So kernel here appears here, and this explains that the movement of the alpha stable process is decay polynomially. And if x and y is close to each other, then 1 over distance goes to 0, so the minimum will be, these are close, then it goes to diverge. So the time variable explains the process. But if the points are different, very large, then it's the movement of the alpha stable process appears time times the jump, the corner. Now we move to the Feynman perturbation. We first consider the simple process, which is a Brownian motion corresponding to this Laplacian, and we put T as the semigroup of the Brownian motion. And we consider the measurable function Q satisfying the following condition, which is Kato corresponding to the Brownian motion. So the expectation of the QB up to time t integrated by t, and it is uniformly converged to 0, where t goes to 0. Under this condition, we can perturb the generator with using the function Q, and the Feynman-Cock perturbation TQ is well defined using the extra term. So we want to add some extra, which is good function satisfying this Kato condition. Similarly, we can also perturb this operator by the measure mu with the kernel Q. Then we similarly define the Feynman-Cock semigroup using this measure mu with the same explanation.
What does a Kato condition mean?
So that means if intuitively the mean of this very small time, it converges to zero. So actually this exponential means this means the summation of the scale of those, the series. This is a series of these exponential terms, and this means the large case scale of this converges to zero. So the summation, this guarantee this is a finite, well defined in mathematically. And we can obtain the transition density of this Feynman-Cock semigroup with the function Q has the following upper and lower bound. So you can see that we have the exponential term, which is a Gaussian function, upper and lower bound, and we need the extra term, which is e to the minus k1 and e to the k2 with time t. So the finite time variable, then this exponential term is just constant. So we can say that the heat kernel is comparable under the Feynman-Cock perturbation. So we call this is a stability theory for the Feynman-Cock perturbation. More generally, we can consider the measure which is similar to the previous Kato condition, but we use the density function. So this is a density function, so that this is actually exactly same as the expectation of the Brownian motion with the measure mu. Because I just interchange the notation, this previous definition with the expectation to this notation, integration up to RD. Maybe here I use the RD. And the heat kernel, this is the heat kernel of the Brownian motion I wrote down here. So the definition is exactly same, but I want to use the measure mu. So I use the following notation to denote the Kato class. Then we can find the functional, continuous additive functional corresponding to the measure mu. I denote here by a mu, and this has the following observation. So there is one-to-one correspondence between mu and the functional a mu, that the expectation a mu is explained by the measure mu for B, Brownian motion. So this functional and measure has a one-to-one correspondence, and under this condition, we can consider the Feynman-Cock semigroup using this functional. So in the previous slide, it was explained by the integration with the Q, but here we consider this functional, and then we have the density which has the same bound as 1. So this is the another way to describe the Feynman-Cock semigroup using the measure mu. And for the measure case, measure-wise, we define the Kato condition following. Now we consider the more general case with the process. Here process X is the Markov process, and then we consider the Kato condition which are same in the Brownian motion, exactly same. And then we define the Feynman-Cock semigroup of those, and it is well defined. So in this case, not anymore the Brownian motion, but it can be the jump process. Then For example, we consider the alpha stable process. In this case, we also consider the measure mu satisfying this Kato condition using this density function corresponding to this alpha stable process, and we consider the functional a mu corresponding to this mu. Then we can perturb the operator by the mu, and then we get the Feynman-Cox semigroup using this notation. Then we can see the density is comparable to the alpha stable processes for the finite time variable. So you see the same observation also holds in the Brownian motion case, that the density of the Feynman perturbation from the alpha stable process is comparable with the density of the alpha stable process with some extra exponential term. So we say that also this is the stability theory for the Feynman perturbation for alpha stable process. Okay? I can say that again. This is the density of alpha stable process. And the first finite time t, then this exponential term is just constant, comparable with the constant. So we can say that these two are comparable, similar. So under the Feynman-Cox perturbation, we have the stability theory for the Kernel estimates. Now we consider non-local Feynman perturbation. Previous one is the local, which is the continuous Feynman perturbation. Here we want to consider the jump type of the perturbation. So here we consider X is a Hunt process in C11 open set, and we consider it has the density comparable to the following three. Here we consider the certain open set D. So the heat kernel of this Hunt process is decomposed into the three terms, and the last term, this last term, is the exactly same as the alpha stable process in global, in RD. But we need this extra two term to describe the exit time. So here delta dx is the distance between the point x and the boundary of D, or the complement of D. So this explains that when x is near to the boundary, then it decays according to this rate. But if x is far from to the boundary, then the minimum of these two will be 1. So it is comparable with the original one. So this explains that how the process move when they are near to the boundary. So this is the assumption. X is the Hunt process in D, and it has the density which is comparable to this. Then Hunt process is the large class of the stochastic process. It included Levy or Markov process, yeah, or more general, yes.
But why do you consider square root of D in the denominator?
We need,
Scaling?
actually, sometimes we use the alpha and 1 over 2. Delta dx alpha divided by t and take the 1 over 2. So, yeah, so actually the alpha stable process, so we have the alpha here and we take the 1 over, the scale of that.
Okay.
It's more intuitively understandable. And then we perturb the operator using this operator, A mu f, where A mu f is the sum of A mu and the function f, where mu is the same one, the signed measure, and f is the function vanishing on the diagonal. That means there is no value if x and y are same. So this describes the jump at the point S. That means right before S and the right after the jump, at the jump. So this term describes the jump of the process. And using this functional, we perturb the operator. And then we can define the semigroup using this new functional. So we call this, it has the non-local Feynman perturbation. This describes the continuous part, and this part describes the jump part for when they are perturbed. Then we can find the estimates of the density of the Feynman-Cox semigroup described by the same function, because we only consider the finite time. So in the finite time, the original heat kernel is describe the density of the Feynman-Cox semigroup. So still we can see that the stability theory under the Feynman-Cox perturbation, not only the local but also non-local case. So what is the next question? Now we consider the Hunt process corresponding to a density P, and then we want to perturb and then define the Feynman-Cox, and still the heat kernel will be comparable. The original one and the new Feynman-Cox semigroup density are comparable in general. This is the next question. It is always true. So to get this, we observe our motivation process, which has the local part and the non-local part. In the previous slide, we only see the Brownian motion, which only has the continuous part, diffusion part, and we consider the alpha stable process, which only has the jump. But here we want to consider some of them. So this process has the continuous part and also the jump part. So to describe that, we define the matrix A, which is comparable with the scale of those. So when we consider this is a derivative of each coordinate, then actually this matrix is comparable with the Laplacian. So we consider a matrix which describes the operator comparable to the Laplacian first, and we consider the function psi, which is a strictly increasing function satisfying the following weak scaling condition. And then define the jumping kernel by 1 over the distance of xy with d and 1 over psi. So this means that the function covers the diverse exponent from beta 1 to beta 2. If these two exponents are same, then it is exactly similar to the alpha stable process. But we want to cover all index between beta 1 and beta 2, where these two are in between this 0 and 2. So this describes the jump part of the process, and this describes the continuous part, because we will consider this operator LC and LJ, some of those, which LC is the continuous part with the operator A, and LJ is the describe the non-local part. And we know that the heat kernel corresponding to this operator L is obtained the following equation. So it looks really complicated. You see, this means the minimum of this and the sum of this. And here the first equation only has a time variable, and this is the Gaussian function, and this looks like the jump. So more precisely, when we see the function pi, which are introduced in the previous slide, is decomposed into the near diagonal estimate. That means R is really small. That means R is small means this is really large and this is large, so that we only have this first part. So the near means the x and y are close, R is small, we have this observation. Otherwise, we have the estimate by sum of the diffusion part and the jump part. Whenever this psi r is r to the alpha, then it is the heat kernel of the alpha stable process. So this observation, the Chen and Kumagai obtained the heat kernel for the sum of the diffusion and jump process. And we motivate this process. So here we consider the general metric measure space. In previous observation, only consider the RD, which are Euclidean space. Now we further general space, that is the locally compact and separable metric space. And the full support, which means the support of M is M. And then to measure the ball in this space, we define the function V, xr, where r is the measure of the bore, the size of the bore, radius, and center x. And we assume this function v has the following volume doubling condition and reverse volume doubling condition. That means 2 times of the r with the radius, the size of the bore is bounded by the size of the bore with the r some constant. And the reverse one means L the bigger than 1 with L times R is bigger than the size of the bore with the radius R with some constant C. And these two conditions implies that equivalent to the ratio of this size of the large R and small r are comparable with D1 and D2 for some constant D1 and D2. So in Euclidean space, D1 and D2 are same as D, but we covers more diverse metric space. And we assume another strong condition, that is the uniform volume doubling. To get the calculation easy, we need this condition, but in general also this holds. But some part does not hold, but we need some point, we need this uniform volume doubling condition, that is wherever the point are, the volume, the size of the bore are same. That under this uniform volume doubling condition, we can construct the process X. So we consider the Hunt process X in M with the density P, and we need to give some condition on P. We explain two functions pi c and pi j. To describe the condition of P, we introduce two strictly increasing function pi c and pi j, which is satisfying the following weakly scaling condition. So here, pi c, and I use the notation with the tilde to describe that this is bounded by G with some constant C and vice versa. So that means the ratio with the two different large R and small r is comparable with two different constant exponent beta C1 and beta C2, and this is also for holds using the exponent beta J1 and beta J2. So actually we extend the previous observation by Chen and Kumagai. So this describes actually the continuous part of the process. So I put this as a pi c to denote the continuous, and we put the j to describe the jump of the process. So this means actually in alpha stable process is this beta will be alpha in between 0 to 2, and usually in this diffusion case it is the equal as 2. Okay, so we can assume the following condition. If you consider this pi c as R2 and pi j is considered as the R to the alpha, where alpha is in between 0 to 2, then when R is less than 1, it is generally bigger than pi c. You consider this pi c is considered as alpha 2, and pi j is considered as R to the alpha, where alpha is between 0 to 2. Then in general, R is less than 1, then pi j is bigger. And if R is bigger than 1, then pi c is bigger. So we assume this property and define pi r by the minimum of those. So in R is less than 1, we have this is exactly same as pi c. So the process controlled by the continuous part. And if R is larger than 1, which means the point x and y is far, then it controlled by the jumping part. And then we can also find the function pi bar c, since we assume this pi c1 is bigger than 1. We can find this pi c bar function, which is comparable to pi c r divided by r, which means it is considered as the r, because we consider this pi c as r square, so it will be r, and it also satisfying the following weak scaling condition with the minus 1. So using this function, now we can give the assumption on the heat corner. the transition density. That means this is bounded, comparable with the time variable and minimum of the sum of the continuous part and the jumping part. Here PC is the continuous part. Describe the continuous part, which is this V we consider the dimension D, and this we consider 1 over R to the 1 over 2, and this we consider as the lambda with D square divided by T, because this is we consider as the R. And then inverse is just still R, so this we considered as D square divided by T. So actually this is a generalization of the diffusion case. And Pj is described again the minimum of the near diagonal and T times of the jumping part, jumping corner. So under this condition, we see that the process X has a jumping corner given by 1 over distance with the D and the distance with the pi j. And pi j is comparable with it has the weakly scaling condition. So this is our condition. We want to find, we will do the Feynman perturbation for the process X, which has the density comparable with the following term. We know one example of those by Chen and Kumagai, so we can focus on this process. And then similarly, we will define the Kato condition. But we need the new definition because this is a new process. We need a new definition for the Kato. So we consider the measure mu and Feynman, the additional functional, additivity functional A mu, which is defined in the following. And we consider the function f, which is vanishing on the diagonal, and define the function AF by sum of those. So we consider the continuous Feynman perturbation and also non-local part. And then we define the AT by sum of these two, define the Feynman semigroup. So next question is, what is the Kato? We need the Kato condition, and under which make the stability theory of the Feynman semigroup. So to give the definition of the Kato, we introduce new function G lambda and H. Actually, G lambda and H are really similar to the function P C and Pj, but we use pi. In previous slide, it was a pi c, and in previous slide, it was pi j, but we formulate only pi because it's much simpler to calculate. And then we prove that the Kernel condition, which are given, is actually similar to this function g and h. And then we can control only these two functions, much simpler case, because previous one is the pi c and pi j, so it is difficult to compare these two functions. But since they have the same notation in this, so it's easy to compare later in the calculation. And then we put this sum as the pi bar. Here lambda is this constant. So here is the definition of the Kato. To describe the Kato, as we see that we want to find the limit of this soup. And the same as the previous one, we put this is as the density upon row bound of density, so estimates. And also here we put the density, but here mu for the Kato condition for the measure, and this is the k, which is described by the function f and the jumping corner j. Since we consider non-symmetry case, we need this add with j, w and j, and we product with the corner j. And then the second Kato condition for the measurable function f is the limit of this in 0. So this is the two Kato condition for mu and f. So we put them as k for the measure and j for the function f. And we use the notation if mu is in kato and f is in kato j. Okay. So this is our condition for the kato. So we assume these two conditions K1 and K2, which means mu is a kato class and F1, which is e to the F minus 1 is in J. So this is a weaker condition than F is in J. And under these two conditions, we obtain that the existence of this Feynman-Cox semigroup, and it is the strong continuous semigroup in L2. And next question is the stability theory for the Higgs corner. To get that, we need these two conditions. The first one is the convex condition on pi bar C. But the convex condition is also clearly true for our example, because it is R, which is the convex. So we need this condition, and this is intuitively natural. And the second condition is beta J2 is less than beta C1, and beta C1 is 2 in our example, and this is alpha, which is less than 2. So still, this beta condition is natural, intuitively clear. So under these two conditions, we finally get the estimate for the Feynman-Cox semigroup. So we fix the time t, and we consider the process x on M, and we consider the density P satisfying the Higgs corner condition. Then under these two Kato condition and the convex condition and beta condition, we find that this is a semigroup in L2 and it has the density which has the upper bound in the following. So this describes the Higgs corner by G and H with some constant, and we consider the for large t, so we need the extra exponential term. And for the lower bound, we need the extra condition that JF is in J. So here K2 is just F1, which is e to the F minus 1, which is a weaker, but for the lower bound, we need the F is in Kato. So this result gives us that the stability theory for the Feynman-Cox semigroup. And as the application, we also get the parabolic Hanach inequality, which is the potential theory for the PDE. So we first give the definition of the parabolic. But here, the parabolic function is new because we need the parabolic when we perturb the Feynman-Cox. So we first consider the process x, theta s, which is the two variable, which is x is the same as a space process, and vs is the time process. And this comes starting from the v0 and it go backward. So sometimes they use the plus, but it's depending on which notation you use. But we choose this notation because it's easy to get the calculation. And we use the notation ptx as the row of the theta s from starting from at t time and x in the position. And we use the tilde tau s is the first exit time of the time space process theta. That means the infimum time of the process where the process is out of the d. And d is a subset of the time variable and the space variable. Then we call the function psi is the parabolic if we consider the point A, B to denote the interval in time variable and the radius r and point x0 with the ball. We consider the set D. And this is a parabolic, mu f parabolic, if we consider the expectation of this, which is the Feynman-Cox semigroup, but the time at the time exit time of the D1, where D1 is the relatively compact open set in D. So this expectation is exactly same as the original function with the starting time. We call this is a parabolic.
Of course, why it's not called parabolic?
Actually, I I cannot give the correct answer because it comes from the PD analysis view.
PD theory, you call because there is a symbol you apply Fourier transform.
Mm-hmm.
You know, utilize this polynomial for symbols.
Uh-huh.
There should be something related.
Actually, we put the definition originated from the other process, not the Feynman one, just the original process. I guess this the next result can explain the reason. So we just define the definition of the parabolic function, and we consider the quantum process under the following HK condition and convex condition, beta condition, and also the Kato condition. It should be Kato condition here. And then we assume mu is in Kato and F is in also Kato. Then we have the following inequality. That means for the parabolic function is comparable with the two space which Q1 and Q minus and Q plus, which is describe Q minus describe the small time variable, and Q plus is the large time variable, and the space is quite similar than the whole space. So we can comparable this function in those set. Then we have the parabolic Hanagh inequality. Yes. So we can get the answer for the parabolic Hanagh inequality for the Feynman perturbation, which is the first observation in Feynman perturb when we perturb the process. So I guess I stop here for the lecture today, and thank you for your attention.
There's many questions from you. So please just ask questions, comments, remarks to Professor Kim. Maybe let me start with a question. At the very beginning, you mentioned relationship of this transition density in probability and also, a solution of a heat equation in PD. And what's the relationship of a PD and this and in your Feynman perturbations? I think you also mentioned Schrödinger operator, right? So can you write down the differential operator in your most general perturbation?
Okay. Here we see the Schrödinger operator, which relates to the Brownian motion or the Laplacian.
Yeah.
So we can change this part into L, which is LC plus LJ, and perturbed by the Q, which means we perturbed by mu, and also we additionally some part which can be described by the double integration because it describes the jump. So actually there is a result I have to write down here. We also find the generator of the corresponding generator of our
Which means
process.
people can use your theory to solve PD problems.
Sure.
So you are a PD guy.
If you accept me join your group, then I'm happy to.
Okay. Any questions, comments? Please.
Yeah. Is there an intuition of the fractional Laplacian?
Fractional Laplacian?
Yeah, the power of the Laplacian.
Ah.
Yeah.
You mean alpha, right? Alpha.
Yes.
Because in probably point of view, definitely this is related to the non-local operator, so it gives the answer for that. And also for our case in probability, this is a jump process, pure jump process. So there are many needs to describe the not continuous case. We need to describe the more diverse and case in word, and then there are many needs to get such a to describe the jump. And the typical example was alpha stable, but not only alpha stable. For general, the Levy with the jumping kernel J, we also get So we want to find the answer for diverse process, not only the alpha stable.
So it is considered as the power of the operator. So what happens if the somehow square root of operator 2 times, then you get the full operator?
Yeah.
I think I can answer Professor Park's question. So at the very beginning, you define the fractional operator by using the interpolation space and also fractional operator by complex analysis. And then in the end, you ask whether there's an XP formula, like the convolution with some kernel, and then in the end, they found this formula. Okay. Yeah. And now she's using the viewpoint of the Brownian motion, this very microscopic viewpoint to explain this fractional operator. Can you tell us some application of parabyte 100 inequalities?
I'm sorry. I mean, actually, I know it is popular in the PD.
Yeah,
they
super popular.
want to the estimates. So we put them in the final section to describe. And I know it is well connected, but not really in the probability point of view. Sorry, I don't know.
I see. For PD, you can derive bounds, a priori estimates, and maybe you can derive uniqueness from this inequality. That's very useful. Good. So, other question, comments, even counter examples? Could you see it? But maybe that may answer a question for the student. Because I think in your talk, you use a lot of very many advanced theory real analysis. Do you have any advice for those students who are learning real analysis? And if they want to, pass the real analysis, if they want to do research in probability, do you have any tips or any suggestion?
For the meta theory and real analysis?
Yeah, I think who are learning, who are taking course in real analysis now? Please raise your hand. A lot of students. Yeah. I think some of them are very afraid of this topic. And do you have any tips?
Not sure, but I guess some of you learned the Brownian motion. Have you learned Brownian motion yet? Or martingale?
Martingale?
Major theory?
Radon major? Not yet?
And major theory, L1 space. What is okay.
But I think this is a very good talk to illustrate the potential application of real analysis. The Brownian model is very important if you want to earn money from stock market, right? For example, if you want to study stochastic, PD, for example, and you
in the the stock market graph is described by the modeled by the Brownian motion. The stock market looks like it's continuous, but it has a lot of tick, right? Which means it cannot be they don't have the derivative. This is the property for the Brownian motion. So this stock market described by the Brownian motion, and in real world, lots of things can described by the Brownian motion because Brownian motion has a randomness. So uncertain this situation can describe using the random variable. So that's the reason the stochastic and or data science, they are interested in the random variables because this uncertainty can model or describe by the such a process. So the starting was the Brownian motion. The Brownian motion, actually the Brown is the biologist. They find some pollen in water. They find that the water molecule makes some changes, this pollen in the water. And then Albert Einstein finds the paper by this heat equation, the previous slide heat equation, Einstein paper. And after that, Chung, I guess, he got the Nobel Prize. He find the existence of the atom and molecules. So from the Brown is 80 something years, and he find some pollen in the water, and they move. And how they move? They just find the movement, and then after that, we find the existence of the atom and molecules. So it's starting point. The Brownian motion is starting point, And then recently also the probability got the Nobel Prize, actually it's math, in math. Nobel Prize according to this probability theory. So it's really interesting if you're interested, that it also can be applied in the stock market or data science to expect the future.
Yes, very nice. And also, because today you also mentioned jumps. Can we see jumps in stock market?
Actually, we...
And my conjecture is a Trump give us a jump.
Yeah, that's the
is that
reason,
true?
that's the reason we want to consider the jump in the random variable, because about Brownian motion is a continuous one, so it changes not smoothly, but it changes continuously. But recently we can find a very big jump in stock market. So we need new process to describe. So not only the one factor, but diverse factor also affects the price, for example. So the process is getting difficult, getting complicated. So we start from the very basic one, which is the Brownian motion, but we add Brownian motion and continuous function and continuous, and add some extra, add some randomness to expect the future.
Very nice. So, questions, comments, remark? Okay. Yeah, if it is not, then let me summarize. Okay, according to my opinion, I think Professor King's idea and this Brownian motion research is an intersection of PD, okay, probability, and also if you want to become a rich man, okay, if you want to work in Wall Street, this is very important, the fundamental tool to study stock market. Okay, if you don't have further questions, the last thing, Professor King. Thank you.